know it's been a long day. The presentations have been great. I also am suffering a little bit from jet lag, so I'm trying to get myself up a bit here to make sure that I'm going to do justice to the material. So I'm an engineer at SysDig. If you haven't heard of us, we make a security and monitoring platform, and our tagline is that our goal is to help users confidently run cloud-native workloads. So recently, myself and a few engineers that are here have been working to add support for PromQL into our existing monitoring platform. And I wanted to share a little bit about what we've learned about PromQL and the Prometheus data model and supporting the Prometheus remote read API. So I need to give you a little bit of information about the SysDig setup. There we go. So SysDig's monitoring platform looks like this. We have a software agent that runs on a host, and it gathers data about the system and about the processes and containers that run on the system. And that includes system-level info like CPU usage and memory usage, but we also collect metrics from any applications that are running there, and that includes JMX, StatC, and of course Prometheus. Well, the agent gathers this data and then pushes it up to our backend. And we gather data roughly every 10 seconds. We typically push it up to the backend immediately after we gather it. So in our backend, it's stored there both in the original form that we collected, but we also downsample the data to make large queries more efficient. In our backend, then users can view and slice that data in lots of different ways, per cluster, per deployment. We do things like supporting RBAC. So if you're a user, you have a very specific slice of the infrastructure that you can look at any given time. So we have a lot of features, and we have customers that like what we do. However, what we can't do today is that we can't perform arbitrary math operations on the data. So hence, that's why we wanted to add PromQL support. And specifically, we wanted to support the Prometheus HTTP API so that in our own UI, inside the SysDig UI, we can make calls to that API, but also our customers can use other visualization tools like Grafana. And that API will connect to a PromQL engine that uses the PromQL evaluation code from Prometheus. The PromQL evaluation engine that we have named the PromQlator will talk with our data store via the remote read API. So let's look at some examples of what PromQL asks from the storage layer. Here we go. So here's an example. This is a range query from T0 to T1 over a 10-second step, and it asks for instances that have been up. So what the storage layer sees, and when PromQL parses and sends a request on, is something that looks like this. There's a set of label matchers where the name is up, the env equals prod, and then there's a request time. And if you look closely, you will see that, very interestingly, the start time is not T0, it's T0 minus 5 minutes. So the first question I'm going to talk about, the topic I'll talk about is, why does it ask for this extra 5 minutes? And what does it mean for people like us that are trying to make PromQL work with some existing data? A second example here is, again, another range query. And this time it's running a rate over a specific metric. And if you look at what the storage layer sees out of that request, you see the name matching. This time you see the start and end times, T0 and T1, that actually match up. But then you also see this other interesting section called read hints. So the second and third topics I'll talk about are, what's a func hint? Right? Why is that information being passed along? And then what does rate mean? Why is that passed along, and what's the implication for the storage layer to respond? Okay, so let's talk first about the 5 minutes. As you know, so the Prometheus scrapes targets, it obtains samples, and stores results as sets of time series identified by different labels. And so this is the Prometheus storage model. Now, for each job, samples should be roughly a scrape interval apart, but that varies depending on the response time of the target, the system load, network conditions, and so forth. And even if targets have the same scraping interval, they'll have different starting points. So there are lots of reasons why the time series in your store have samples that don't line up with each other. So this has an impact to how PromQL evaluates data queries. So let's talk through the two data queries that you can do in PromQL. There's the instant query, which says, given some PromQL expression, evaluate it at one point in time. And there's a range query, which takes a start and a step and end, and it evaluates the expression you give it at each step along the way. And a range query logically just works like it's a sequence of instant queries. In either case, consider what happens if you try to evaluate a PromQL expression that references a time series and there's no sample at the evaluation time. Right? So what happens? Well, it depends on how you reference the series, and there are, again, two ways that this can happen. One is by the range vector selector, and that's the syntax you'll recognize with brackets. PromQL will look at the duration that you specify and then use the samples starting from that duration before the evaluation time. And then it takes those samples as input and feeds it into whatever function you're specifying this range vector selector to. And then there's the instant vector selector. And as the name suggests, it's looking for a value at a particular instant. Okay, but chances are there won't be one, right? Just because of how your samples line up. So then what does PromQL do in this case? Well, what it does is it looks for the most recent value found at or before that evaluation time. Right? So in this case, it'll go back in time, find the sample that was closest to your evaluation moment, take its value, and then act as if that value occurred at the evaluation instant. And like I said, instant queries are just range queries are just instant queries repeated over time. So the same logic applies at each step, right? So if you do some range query referencing lots of series, it'll just go and find the most recent value and push it forward. And the benefit of this is that it lets PromQL work with aligned values between samples, so you can use that for your calculations or for comparisons as you interact with the different series that are there. So maybe you're wondering, well, how far back does it look? Right? I mean, to phrase differently, how long do you see the value of the last sample? Well, it's controlled in, again, two different ways. This seems to be a repeating pattern for PromQL. So the first way is via something called a configuration setting in your Prometheus server called lookback delta. Can I just get a show of hands? Who here knows about this? Like, who here has actually configured this? Okay, great. I'm glad it's not everyone that I'm like, oh, this is so fascinating. And, okay, so the default value of this is 5 minutes. And this is where that extra 5-minute request came from in the storage layer request. Right? So, and again, same logic for range queries. So what this means is that if you do a range query and the alignment logic says that it's going to use the lookback delta process to find the value, you could see this odd-looking repeat of the value across a straight line for 5 minutes. And consider what this means for alerts, right? So if you had an alert that was supposed to fire if there was no value for a series, something like alert me if there are no application instances, you would be waiting 5 minutes before that was actually noticed, right? Because your evaluation would just keep saying that, yes, it looks like it's up. Okay, so chances are you have not noticed this 5-minute delay, right, in your alert processing. So what else is going on? Well, the second way that PromQL manages scrape samples is with something called stale markers. Who here has heard about stale markers? All right. About a third, I think, in terms of the people that are looking at. So during scraping, if a series isn't seen after some scrape interval, then the scraping logic adds a special sample called a stale marker. It's encoded with a special floating point value, a stale nan. And if PromQL sees this value, it won't try to create those extra values after the stale marker occurs. So it's not like a permanent tombstone that you might think about in works like Cassandra, right? It can appear multiple times throughout the time series just based on if the target, the instance that's creating that series comes up, goes down, comes up, goes down. So this marker is never seen directly by users of PromQL, right? And PromQL ignores this marker for anything except this very specific usage of finding out what value to use at the evaluation time. So what does this mean for us, right? For Sysdig or for people that are embedding PromQL in front of other data? Well, it matters for us because we have data that did not originally come in via Prometheus scraping. Right? So we need to ensure that the read responses we give back to PromQL have the stale markers where needed to make sure that users see the same type of graphs and the same type of alerts that they would see with Prometheus. So since we're adding this functionality into our existing systems, ones that already have data, we have to do a mix of actions here where for some metrics, we'll add stale markers as we gather them from sources like Prometheus metrics, but for other metrics, like those that already exist in a customer's data store, we'll have to dynamically add them in at query time. Okay, so coming back to our questions, so now we know why the PromQL asked for that extra 5 minutes of time before the start. So let's go on to the second question here. Why does PromQL send this ask for, or send a hint here called func? Well, the answer has to do with downsampling. So again, show of hands, who here uses a downsampling system? Presumably, probably Thanos in this room, but maybe Sysdig too. So, okay, not a lot of folks here. Well, think of it this way, right? So let's say you scrape a series once every minute, which I think makes sense. Scraping intervals, I think, are typically in the order of a minute or maybe less. If you want to graph that data over a month, right, for each sample, that's about 45,000 samples. That's likely more pixels than you actually have on your display, right? So why pay the resource cost in terms of the CPU to evaluate the expression and the I/O to load all that data when most of them won't make a difference to what you actually see? So what you can do is instead of using the data directly, you can store an aggregation of those scraped samples. Right? So you break up your samples into windows of time, like 5 minutes or 1 hour or whatever value you want, and you store some representative value of all the data that occurred within that window. And then you use this aggregated data instead of the raw to give you answers that are close enough for many use cases and that conserve resources at the same time. So if you do this, what representation should you store right within that window? I mean, you can go and calculate an average, which might work for many cases, but as we heard, kind of max is very important, especially if you're looking for peak usage. So maybe you'd also want to store the maximum value instead. And you can come up with lots of other use cases where you really want more than one representation because you want data to specialize for a particular type of query. So there's no constraint to only store a single one of these aggregations, right? Because we're not doing this to save on storage costs. We're doing it to reduce the cost of these large, wide queries. So now, if you store multiple of these aggregations, how do you know which one to use? Well, that's what the hint is for, right? The hint, when PromQL makes a request to this for a particular series to the storage layer, it looks at the function or the aggregation that surrounds that reference, and then it sends that along as a hint. And it's actually called the surrounding function hint. And then downsampling systems like Thanos or Sysdig can use this hint to select which aggregation to use to satisfy the request. So if the surrounding function was max over time, we'd use the max aggregation, for example. So hopefully that makes sense. So then to the last question, well, what about this rate hint? So what kind of aggregation would you use to satisfy a rate hint? Okay, to answer that, we need to understand counters, and we need to understand the rate function. A counter is pretty simple. It tracks the occurrence of an event, right? It starts at 0, and increases from there, or until something happens, and then it resets, and then it starts over again at 0. I really like this. So here's an example counter series from Prometheus. Right? Each of these values represents the number of events since that moment from the start of the time series or from the latest reset. Any decrease in value here is interpreted as a reset since we may not actually sample the counter right when the 0 occurs. And resets happen, as I said, because application instances may come up, go down, come up, crash, go down, and come back up. Right? So you just see these resets over time. The rate function in PromQL is the most common usage that you talk about for counters, and rate divides the change in the number of events by the change in time over some interval. So what you really need, since getting the difference in time is pretty straightforward, the tricky bit is finding the difference in the number of events. So how does rate do this to calculate the difference in events? Well, if you look at a section where there's no resets, it's pretty straightforward. You can sum up all the deltas between the samples. Right? So you just look at the difference between the first and the second, add that to your sum, and then you keep doing this all the way along to get the difference between the last value and the first. If you have a reset, you add the post-reset value, and that's because that reset, again, represents some number of events since at 0 that occurred, in this case, that you didn't necessarily see. So you add up all those values. And effectively, I like to think about this, you're just transforming the series by sliding up everything after each reset. And if you look at kind of these high-level values, again, if you want to get the difference in events, you can just subtract the first value from the last value, and that tells you the difference. So what kind of aggregation would you need for rate? So immediately you can know that average won't work. Average won't work because you'd probably lose some resets just depending on the data that actually occurred. So let's walk through a simple example of just comparing two windows. So how many events occurred between T1 and T2? Well, first thing we can think about here is that what we really want, we're really asking is the difference in events between the last value in T1 and the last value in T2, right? The events before the last one in T1 don't make a difference. You just get rid of those. And with the values that you're left, then you can now calculate the difference in events just accounting for resets. And you do the same process that I mentioned before, slide them all up, and then sum up the values that you have there to actually get that last value. And again, if you'll notice what's happening here, it's a little hard to, I think, see up here. It's you're summing up all the values that occurred within the T2 window. And if you store that sum, that's what you actually need to effectively perform the rate calculation. So in this case, we just needed the last raw value of the window before and the sum of the events in the window we're looking at now. And with just this, you can now subtract those two, and you've got the difference in the number of events, which is exactly what rate means. So the point here is look at the last raw value, look at the sum of the events. But that's not all you need. So let's walk through one more example. So let's do this case where you go from T3 to T4. We can do the same thing, right? Only the last value in T3 really makes a difference. We can sum up everything that occurred in T4. And now you would think, well, can you just subtract the difference from the last value, the last sum that you calculated in T4 to the last value in T3? And the answer is you cannot. And you cannot because there was a reset that occurred between T3 and T4, right? And so what that means is that just the events in T4 actually make a difference. So to summarize here, what we've said is what you need the sum. You can go through all of your samples, and you need the sum of the events in the window, the first raw value, and the last raw value. And you need those raw values because you need to be able to recognize when counter resets occur. And that gives you the information you need to calculate the difference in events between windows, which is great. But that's not exactly what PromQL asks for. It actually asks for a series of values over time. So we need to turn this into a response that we can give back to PromQL. And the way this works, at least in Thanos, is that it looks at the data that was stored off of that aggregation, and it constructs, by adding up these differences over time, this really nice monotonically increasing value that goes up in time with no resets. And this is exactly what PromQL wants, right? You could handle the resets if it needed to, but it's now given it exactly the values it needs so that PromQL can look at the difference between those two. So that was the last question, right? To use rate with downsampled data, you need something like a specialized counter aggregation in order to make sure that you're giving the correct and accurate answers back when you look at downsampled data. And then how this matters to us is that, well, we need to make sure we support that specialized counter aggregation. And of course, we'll do this for Prometheus metrics. But very interestingly, again, since we have data that did not come out of Prometheus, we can now use similar techniques for other non-Prometheus data in our system. And that means that users can use rate even with non-Prometheus data, because we know exactly how to represent it to PromQL to make sure that it gets accurate answers. So that's it. I hope that that little foray into PromQL and the Prometheus data model has been interesting. I'll be happy to take any questions about what we've been working on. Thanks.
Good. Thank you. Who wants to box?
What was the bug you discovered in Thanos?
Go back. The boundary align reset. Right. So it was just a matter of you need to store the first raw value too.
Thank you.
And thanks to Alexander, my colleague, who spotted this problem. I just coded up some stuff to fix it.
Yeah. Thanos was storing the last value, but not the first, for clarity.
Have there been any PromQL expressions that were hard for you to PromQlate, or that you think they might be hard to translate?
To translate it for what we think, not yet. The counter is definitely the one that just requires some more thought, the most thought and thinking. I mean, an advantage of what we're doing, we really are taking the exact PromQL code, right, and we're just creating a service out of that. It supports the storage abstraction that's there. The abstraction layers within Prometheus are really nice, so it's actually pretty easy to work with and do this.
Cool.
Any other questions? Okay, well, I guess thank you very much.
Thanks.